Okay, let's start off chapter 5 then, where we're looking at the geometry of autonomous systems. And so today we're going to look at the phase plane of autonomous systems. So you recall back in module 2, when we did section 3.7.2, we talked about the phase plane for autonomous second order differential equations. And so what we want to do today is just generalize that to two-dimensional autonomous systems. And we can do that fairly straightforwardly. So remember, a two-dimensional autonomous system looks like x prime equals some function of x and y prime is some other function of x and y. And so remember, when we did section 3.7.2, we had the special case where x prime equals y. Right, so then y prime is x double prime, and that's how you did second order differential equations. But we're going to look at the general case today. And so we know to make things work, we need like an existence and uniqueness theorem. And we have one for two-dimensional systems. It's quite a nice one. So let's say we have some region R of the xy plane. We have our autonomous second order system, two-dimensional system, and let's say it satisfies these properties that in that region R, the functions f and g are continuous everywhere. The first partial derivatives df dx, df dy, dg dx, and dg dy are continuous everywhere in R. Then, given any initial condition, so at some time t naught, we have x is x naught and y is y naught, and x naught, y naught is some point in our region R, then there's going to be a unique solution curve through that point for all values of t for which the solution remains in that region R. So, very nice. So here's an example. So here we have an autonomous system, and so we see it's nonlinear. And so the solutions to this is going to be some space curve in three-dimensional space t, x, y. And so here I've given three projections: an xy projection, an xt projection, and a yt projection. And we see two of them gives us time plots of our solutions to x and y. And the first one, our xy plot, looks very much like a phase plane, like we saw before. Okay, so our existence and uniqueness theorem tells us that those curves in three-dimensional space can't cross each other, and that the three-dimensional space is filled by those curves. The two time plots, of course, different x plots can cross itself and different y plots can cross itself, right? Because given an x naught, for different y naughts, there's going to be lots and lots of solutions through any given point. But thanks to the existence uniqueness theorem, the parametric plots of x against y for different space curves cannot intersect. Okay, so this gives us our phase plane. And like before, we now come up with a vector field. So what we do is we take a grid of points in our phase plane and we put a tangent vector to the solutions at those grid of points, and that gives us our vector field. And remember, the tangent for the parametric curve is given by t. The tangent vector is, well, in the horizontal direction, it's just f of xy, right? Because f of xy equals x prime, and so that's gives us the rate of change in the x direction, and the vertical direction is the y direction. So the rate of change in that is y prime, and that's just g of xy. And so then if you take a vector field and you put in a set of representative solution curves, you get a phase portrait. Okay, and that's a very kind of nice way to analyze a system of equations. one more definition is important, and we've kind of seen this already in the one-dimensional case, and so we just generalize it to the two-dimensional case. An equilibrium solution is a constant solution. So it's constant for x and it's a constant for y. Okay, and so for it to be constant, the derivative has to be 0 so that the solution doesn't change. So we're looking to solve simultaneous equations f of xy equals 0 and g of xy equals 0. Okay, these are also known as equilibrium points, fixed points, or stationary points, or critical points are all the same thing. Note that if you have an equilibrium solution, since f of xy and g of xy is 0 at that point, the tangent vector is the 0 tangent vector. So that means in the xy plane, that solution doesn't move. So a single point represents parametrically an entire solution curve for all t. Very nice. Okay, finding equilibrium. So that's the main thing of this section, the main thing I'm going to ask you. So for example, if you have a homogeneous linear system, x prime equals ax, where A is some matrix, and let's say the determinant of A is non-zero, the only equilibrium solution, right, is going to be 0, 0, x equals 0, y equals 0. And we're going to explore those phase planes in the next module. For a nonlinear autonomous system, those equations can be a little bit more complicated, so you can get any number of equilibrium solutions, and sometimes it's easy to find these and sometimes it's hard. So to find vector fields and phase planes and phase portraits and maxima, we use the plotdf command. So in square brackets, we put in the f of xy and the g of xy, because remember that's x prime and y prime. Okay, so the first module question for you today is, let's say we're given A equals 1, 0, 0, 0. So the determinant is 0. What are the equilibrium solutions of this system? X prime equals AX. Okay, so let's have a look at a few non-homogeneous or nonlinear equations. So the first one is a non-homogeneous linear system. So remember, in the mixing problem we had in the last module, we analyzed it when there was just pure water coming into the tank A. And well, what happens if we have a brine solution coming into tank A at the concentration of 0.1 pounds per gallon? So remember, it's coming in at 2 gallons per minute. So this changes the system by adding a 0.2 to the x prime, right? Because 0.2 pounds per minute of salt is coming into tank A. So we want to solve that pair of simultaneous equations. We see a negative 0.06x and a 0.06x, so let's add the two equations together. And so we get 0 equals 0.2 minus 0.05y, so y equals 4. Taking y equals 4, plugging it into the first equation, we get 0 equals negative 0.06x plus 0.3, so x is 5. So that means we have the equilibrium solution 5, 4. X equals 5, y equals 4. So we're going to investigate this in maxima. Okay, so here is the equation plugged into maxima. So let's go ahead and evaluate the cell. Okay, and here is our vector field, and we just click in a few places, and we see the direction of the arrows going towards that equilibrium solution. And we actually see there's kind of some funny things happening near there. I think that's because step sizes are really small, so maybe we're dividing by a really small number, so we look like we're getting some artifact going in there. But it looks like not only is that phi 4 a equilibrium solution, but it's a stable equilibrium solution. So all solutions go towards there. Okay. Okay, so let's look at the next example. So now we have a predator-prey system. X prime equals 2, you can read that. The second question for the module is, I say this is a predator-prey system. Which is the prey, X or Y? So if you look at it and think of it biologically, you should come up with the answer to that. Okay, so this is nonlinear, it's homogeneous. So what happens? Well, the easiest one to solve is the Y prime equation, because we can factor that. We can take out a Y as a factor. So we see that 0 equals Y times X minus 0.5. So Y equals 0 or X equals 0.5. So when Y equals 0, we plug that into the first equation and we get 0 equals 2x times 1 minus x. So x equals 0 or x equals 1. And when x equals 0.5, we plug that into the first equation and we get y equals 1. So altogether there are 3 equilibrium solutions at 0, 0, 1, 0, and 0.51. And so now we're going to investigate this with maxima. Okay, so here I've put the equations into maxima. So I'm going to evaluate the cell. And here we get our phase plane. I'm really only interested in the first quadrant. Okay, so we see 0, 0. And so what do we get? So we've got interesting kind of behaviors sort of going on here. And we can analyze that kind of later. Okay. And okay, and for the third example, here's the van der Pol equation. It's a famous equation, something to do with vacuum tubes, if I remember rightly. Van der Pol was some kind of engineer. So we see that it's we can see that it comes from a second order differential equation. Finding actually its equilibriums is pretty easy. Setting the first equation, for that to be constant, we have to have y equals 0. Plug in y equals 0 into the second equation, we see that x has to be 0. So there's only one equilibrium solution, 0, 0. So let's look at that with maxima. Okay, and so here I've plugged it in to maxima, and I'm going to evaluate the cell. Okay, and here is our phase plane, and let's have a look. Ooh, we get kind of nice. Oh, that's kind of weird. So when we look at this, we see that there doesn't, so 0, 0 is an equilibrium. It seems to be a stable equilibrium. But the interesting thing is that there seems to be some sort of stable curve that that's kind of attract. Oh no, 0, 0 is not stable. Sorry, it's unstable. So all the arrows are pointing away from 0, 0, and if we start away from the curve, it goes towards some kind of, there's some kind of curve which seems like all solutions is going towards. So there seems to be some kind of stable periodic solution. Because remember, if it's on a closed curve, then the parametric curve just goes round and round that curve, and so that gives us a periodic solution. It's called, the technical term for this is limit cycle. So we seem to have some kind of limit cycle going on here. Okay. Okay, so that's it.